you might expect this to be a 16 because we squared everything, but it's a 4 because we don't have to pay because we can have errors in both directions. Right, and there's a way actually to interpolate between this peacock and seacock. So I told you that if you embed multi-class into classification, this multiplication by the expected importance is k minus 1. It's bad. But it turns out that if you embed it and you make seacock run only for the non-trivial t's, so it turns out that if your subsets here might be, your subsets S might be half of your labels, right? So it says that the dynamic range of L sub S is going to be something like n minus 1 over 2 to n plus 1 over 2, or n is b plus 1 over 2 to b minus 1 over 2, or b is the number of rows. So if you fix your t's to be in that smaller dynamic range, you end up getting exactly the peacock analysis. Okay, this is all getting mathematical and esoteric and so forth. So let's stop. Not quite. Right, so there are some things to think about. Right, experiments. Good to know how well this works. There's this cool thing about codes. So Shannon pointed out that if you pick randomly from subsets, then you end up with a good code after just O of log k choices. And there's lots of work de-randomizing that, but theoretically at least it's possible to get by with only O of log k, only order log of the number of labels binary classifiers. Or R1 if you do the squashing technique. Okay, so that's it for the real content. And then I wanted to show you a couple pretty pictures before we finish. So I showed you a few reductions. So this binary classification here is importance weighted classification. And I guess when I drew this picture, I was thinking about this probing one that's going directly to classification, but it's really composing. Maybe the arrow should actually be going to importance weighted classification, right? So it's a question about if you compose two reductions, you get one reduction, right? The analysis has to work out that way. So if you compose costing and probing, you get something that reduces directly to classification. But maybe you don't want to do that. In which case, the arrow should actually be going to here. And then we have this technique for doing multi-class classification using class probability estimation. So that's peacock. Then we have this technique which does cost-sensitive classification with importance weighted classification. That's seacock. And then everything. I guess the blue arrows here mean defaults, right? So all the hard work is on the black arrows. And it's kind of a trivial way to embed everything according to the blue arrows. So we can take any bounded loss classification problem and embed it into classification and vice versa. And then, right, there's some work here, actually. And that arrow is not entirely satisfying. But there is something. Reinforcement learning is actually a pretty hard problem. And then you can embed various things into all bounded loss classification problems. So are there questions about this graph? It's a nice, pretty picture, I guess. Okay, so one thing that I wonder about, well, in addition to trying to precisely define this arrow more thoroughly, cause other learning problems which are not here. All right, so that's that graph. And then you can actually also draw a graph for just error-limited reductions, right? So these are less desirable, but the actual analysis that we get is tighter because there's none of the square root garbage running around. And maybe that's important sometimes. So this is multi-class classification here, and there's sort of three very common methods for reducing multi-class to binary. One of them is ECOC. One of them is this tree reduction, where we just say, the first problem is it the label 1 or 2 or 3 or 4? And then is it 1 or 2, or is it 3 or 4? And this is 1 against all, which I explained to you. This is weighted 1 against all, which I showed you a graph at the beginning about. There's boosting, which you can think about as a reduction. There's this subset classification. So weighted 1 against all can actually be used for subset classification as well. So subset classification is instead of having 1 right choice, you might have 2 right choices. So it might be 2 out of K, or it might be or 2 out of L, I guess, or 3. You might have 3 right choices out of 5, or something like that, right? So it's not quite as general as subset classification, but it's somewhere in between. And you can use weighted 1 against all for that. And then there's this weighted all pairs reduction, which reduces consistent classification to importance weighted classification, so that the binary error rate moving through costing and down here bound to cost-sensitive loss by 2 times the binary error rate times the sum of the costs. And then here's this error to reinforcement learning again, but some more work is required there. Yes?
Yeah, this is probably a stupid question, but where does 1 against 1 classification fit in?
1 against 1?
Yeah.
Binary classification?
No, reducing a multi-class problem.
Right. All pairs. That's what it's called often.
Okay.
All right, so there's another one which I left out here, which is all pairs. So that would be going from multi-class to binary. And I guess that's half of this name. It's this part. So that might give you some idea of how this works. So the way that all pairs works is you take every pair of classes and you make a classifier which is just this class or that class. And in the way that you create the training set from the original set is you just kind of filter on this class or that class. Right? All right, so it turns out that all pairs has a terrible analysis in this sense. Well, it's as bad as 1 against all, and you do a lot more work. The reason why it's a terrible analysis, so the way that you decode for all pairs is you take every classifier and you evaluate it. And then does this label agree with predictions the most, or is that one, or is that one, or is that one? So you evaluate all k times k plus 1 over 2 classifiers. And the problem is that, the problem is you just don't get any analysis any better than this. It's kind of unfortunate. There's another problem, which is, so you can take these analyses, and you can actually prove, so for all the analysis that I talked about today, you can say, if it's the case that my data is actually drawn from this distribution that will be tested on, then the method of transforming samples that I used transformed things into the correct distribution. That's not true about all pairs. The reason it's easy to see this because when you train for all pairs, you're only training on samples which are conditioned on being in class I or class J. But when you test, your examples might be any other class, right? And that means that an adversary is kind of free to do anything he wants, which is part of the whole reason why you get a bad analysis. Okay, so so one last thing is I really like boosting, and you should definitely come to a Rubber Superior's tutorial, which I think is on Friday, not this Friday, but the one after that. So boosting is like reduction, but it's also unlike this because it's not trying to solve a bunch of different kinds of classification problems. It's trying to solve one classification problem. And some clever technique of sort of reusing the learning algorithm over and over again to try to compensate for the weaknesses of the previous runs. Okay, so this is the end. You should understand that the study of these reductions, this sort of formal study that I showed you, is relatively new. Which means that what exactly we can do and can't do is not entirely well defined yet. It also means that if you wanted to work on it, you could easily do that. Right now, what I'm working on is trying to produce some sort of coherent code base so that you can easily use these things, and some sort of coherent tutorial, like in paper form, so that you can read everything that I presented now. All right, so thanks. Are there any questions? Yeah? Are there lower bounds? That's a really good question. So these blue arrows, composed with the black arrows, imply a lower bound of sorts. It's actually it's a little bit tricky talking about lower bounds because boosting is around. And this boosting, you'll see later, implies that you can keep on improving as long as your original classifier, as long as the classifiers you learn are doing something useful. But if you don't allow some sort of adaptive feedback, you can state lower bounds. You can say that it's impossible to go from multi-class classification to binary classification with a transform of less than epsilon. Right? Because you can embed binary classification into multi-class classification, and, do any better. It's actually, the proof of that is actually more subtle than I'm letting on. There's some sort of describing of hypercubes and so forth and talking about cuts through the hypercubes, but there are lower bounds of this sort when you don't allow adaptation. When you allow adaptation, everything is sort of out the window. And there are significant gaps between the lower bounds that you get and the upper bounds that we get. So it may be that it's possible to improve the 4 epsilon. Anything else? Okay, I think we'll take about a 20-minute break, and then I think Steve Smale is going to talk to us.